In this video, we'll begin Chapter 8, which is focused on a concept called hypothesis testing. Today we're going to really focus on the steps involved with hypothesis testing, and over the next few videos we'll move on to the test for a mean, both with the z-test when we know the population standard deviation, a t-test when we don't, and then the z-test for a proportion. So first, one of the biggest and hardest components in this chapter is going to be to understand the definitions and the concepts used in hypothesis testing, and we're going to try to lay these out. But note that this first section is going to be a lot of definitions, so please make sure that you either make flashcards or rewatch this video a couple times to make sure you're good with them. We're going to talk about the null and alternative hypothesis, finding critical values, the 5 steps used in hypothesis testing. Now this differs from the textbook somewhat, but this is what we'll use in this class. Testing when sigma is known with the z-test, when sigma is unknown using the t-test, testing the proportions, and then testing hypotheses using confidence intervals, which is something that we've already talked about briefly. So first, hypothesis testing is a way in which we can make a decision about claims on a population. So this is where we kind of ended the last conversation, the material covered in Chapter 7. We said, hey, assume somebody said something about the population. Let's say somebody said, I think college students only sleep 10 hours a night, or I think that cell phones take 10 seconds to send a text message, or anything, any claim about anything. Hypothesis testing is the way in which we study that claim, and we look at data to determine if there's evidence to support or reject that claim. Now, just as a big picture thought here, typically what we're going to do is we're going to phrase these in terms of claims that we wish to reject. So think about maybe I'm created actually think about this course. I really hope this course has taught you something about statistics. So what I might do to test that claim, my claim is that this teaches you something, is I'll set up kind of a hypothesis that says, well, maybe it didn't teach you anything. And I'm going to try to find evidence that rejects that null hypothesis, that nothing actually happened. So that's the big picture idea, is typically we're going to set a hypothesis that eventually we want to reject. So the first things that we have to do is clearly define who are we studying. What's the population? Who am I sampling from? This is an extremely important and often forgotten step of hypothesis testing, and greatly impacts where the decisions of your study can be applied. We have to state each of the different hypotheses that are going to be investigated. We have to give that alpha, that significance level that we had to give in our confidence intervals. We have to select the sample from the population, and we have to be clear about how we're selecting that sample. Is it randomly sampled, stratified, clustered? Was it a convenience sample? We have to indicate what we use and why we use that. In a real test, a researcher has to actually go out and collect data. Incidentally, this is one thing that's sometimes harder for upper level stat students to understand. Somebody's got to collect the data. Now, it doesn't always have to be you, but we always have to get our data from somewhere. So data collection is a really important part of the research process. After we have the data, we have to perform the statistical calculations and perform the statistical test. And then finally, what I view as the most important piece of this is we have to come to a conclusion. Now, this conclusion step ties in all of the components above. Reach a conclusion takes everything about the study as a whole and then uses all of that information to come to a decision that is reasonable and supported by both the structure of the study and the data that came out of the study. In this course, we're going to really focus on hypotheses on means and proportions. I think in your textbook there's also hypotheses on variation. So you could do a hypothesis test on a variance. Just so you know, but we're not going to cover that in this course. Now we're going to talk about the traditional hypothesis testing method. I'm going to briefly touch on the p-value method. Now the traditional method is one that we can do by hand. It's why we focus on it in this course. But once you get into software, the p-value method is actually going to be much more important. Now I'm going to say that the p-value method is one of the most misunderstood statistics in the research world. In fact, recently the American Statistical Association has started to question this method because it is so misunderstood. So in this course and in this chapter, we're going to try to articulate this a little bit, but just know that you want to be really careful if you're using the p-value method. Incidentally, the traditional method and the p-value method tend to come to the same conclusion, but for whatever reason, it's the p-value method that's taking a lot of heat right now. Finally, there's the confidence interval method. This is exactly what we were talking about at the end of chapter 7. I referenced, hey, after this section on hypothesis testing, you should go back and watch the end of that chapter 7 video where I kind of seemed to go on this circular rant for a while. Check that out because that's going to really inform some of the decisions on hypothesis testing and really articulate what the confidence interval method for hypothesis testing is, which is using these confidence intervals to test those claims about the population and see if those claims are supported or not. Of all of these methods, this is the most endorsed method by the American Statistical Association at this time because the confidence interval method gives some data on what is reasonable to assume in addition to whether or not a particular claim is supported by data or not. Now, a statistical hypothesis is something that is like a statement about a population parameter. So again, something like, I think that the mean of the number of cups of coffee being drank by Americans is 5. Or I think that the average American spends $300 on tennis shoes a year. So we're making a conjecture, a statement about a population parameter, that is the mean amount of money spent on tennis shoes. This may or may not be right. We're going to collect data to determine if we can find evidence for or against it. The null hypothesis tends to be written, and again, in our case, we're always going to write this, as a statistical hypothesis saying that there's nothing going on. So when you see null hypothesis, think nothing's going on, nothing interesting. So the American population is doing whatever the default value is thought to be. So no difference between a parameter and specific value, or between two parameters. If we get into two sample testing, we probably won't in this course, but it's an option. So nothing going on. That is typically a null hypothesis, let's say, in, excuse me, in Are You Learning Anything for This Course? The null hypothesis would say, no, you're not learning anything from this course. The alternative hypothesis, which is H sub A or H sub 1, so the null hypothesis is H sub 0 always. The alternative hypothesis says, well, something is going on. Maybe you are learning something in the course. Maybe you are spending a lot of money. Now, the different ways that the alternative hypothesis can be written, it can be written positively, that is, you're learning something from this course. It can be written negatively, that is, that you are learning less from this course. And taking this course, you know less about statistics than you did coming in. Or it can be viewed as non-directional, that is, maybe this course is changing your knowledge. I don't know if it's changing it in a good way or in a bad way. It's just changing it. So if I think that the true value is below a value, we'd write this as a less than. V is just that number that we're thinking of. So this would be that the average knowledge is less than, let's say, 0. So 0 is my default value of how much you know about statistics. And so this would say your average knowledge is less than 0. You've learned less than nothing in this course. let's say the proportion. So you can write this with any statistic. It doesn't have to be the mean. So the proportion is greater than 0. The proportion of you who learn something about statistics is more than 0. Or we could write about the standard deviation. Again, we're not going to cover this test in this course, but you could easily write a hypothesis about it. And then if it's non-directional, it would just be not equal to. So go on and try pausing. I'm going to show these contexts. Try pausing and writing out the null and alternative hypothesis and see how you do. So researcher thinks that expected mothers, if they use vitamin pills, the birth weight of the babies will increase. So the default average weight is 8.6 pounds. Write the null and alternative hypothesis. Go on and pause and give it a try. So the null hypothesis is that nothing's going on. If you took the pills, your average is still going to be 8.6 pounds. But the alternative hypothesis is looking at an increase in the birth weight. So an increase in that birth weight. So my null is going to be that the mu is equal to this default value. My alternative is going to be that the mean is greater than this value. All right, let's try another one. So an engineer hypothesizes that the mean number of defects is decreased if compact discs, if we use robots instead of humans. So currently my mean number of defects is 18. So go on and pause it and write your null and alternative. All right, coming back, so we've got the null. That is that the mean stays at 18. I used robots instead of humans, and it stayed at 18. The alternative would be that the number of defects decreased, so I want it to go down. So in this case, null hypothesis, mean stays at 18. Alternative hypothesis, mean went down. And if you want to think about that, remember alligator eats the bigger number. So mu is the smaller number. It's down from 18. All right, let's try one more. All right, going through this. So we've got a psychologist, not sure if grades will be higher or lower, so we're not sure the direction, but playing soft music during a test will change the result of the test. So the mean scores are 73. This is the default value. This is my null. And then because I don't know if it's going to be higher or lower, I'm going to write it with a not equal to, because it could be higher, it could be lower. I'm just expecting it to change. This is my alternative. I'll say typically in statistical testing, I advise clients to write not equal to. Even if you think it's going to be higher or lower, this tends to be better statistical practice in general, unless you have a really, really, really good reason to think one direction or the other. All right, so after we state the hypothesis, then we have to choose the statistical test, choose the level of significance, and formulate a plan. Now, the statistical test is going to combine the data in a way that can let us make a decision about our particular case. So a statistical test is going to depend on which parameter we're testing. Is it mu? Is it that u thing? The mean? Is it p? Is it the proportion? Is it sigma? Is it the standard deviation? Statistical test is going to be based on that. Do I know the population standard deviation? Do I not? Now, when we calculate our statistical test, the first thing we're going to do is we're going to calculate what is our number for our current study. So we're going to compare our study to like a theoretical group of studies and see if it's like super extreme. In this case, the value obtained for our study is called the test statistic. So this is the statistic that we're going to be using to test. So the test statistic, again, is something that we have observed. It's something that came from our particular study. So what's interesting about statistical tests, and this is often hard for students to wrap their head around, is that no matter the result of the statistical test, let's say that we decided that actually Americans spend more than $300 buying their shoes after we've calculated our statistics, we could still be wrong. We could be wrong. So what we're going to look at is we're going to look at which hypothesis do we go with. Do we go with the null hypothesis or do we go with the alternative hypothesis? And what we do is we focus our decisions on the null hypothesis. So we either go away from the null hypothesis, that's called rejecting, and go with the alternative, or we don't go away from the null hypothesis, that's failing to reject. So when the null hypothesis is rejected, but it's true, that is, let's say I concluded that my statistics course taught you stuff, but I actually didn't teach you anything. That null, that nothing's going on, was actually true, even though my statistic said it wasn't. That's called a type 1 error. That's bad. My statistic didn't match with reality. My statistic told me I taught you stuff, but I actually didn't teach you anything. So that's an error, and that's called a type 1 error. Let's say the opposite happened. So let's say you actually learned something. Truly, you did. But my statistic didn't catch that. So you learned content, the null hypothesis that said no learning going on is false. You actually learned something. But my statistic didn't catch that. Now that's an error too. It's a different kind of error. We call that a type 2 error. And these really are used. Type 1 and type 2 error, these are really used around the field very commonly. So these are good vocabulary terms to know. To get a feel for this, this is a good graph that kind of summarizes this. This is reality, whether it's actually true or actually false, that null hypothesis. And again, in our case, the null hypothesis is I didn't actually teach anything. So null hypothesis is no learning happened in this Math 115 course. And then my statistic says, do I reject that? Now, if H0 is no learning happened, I'm going to reject that no learning happened. I have to believe you actually learned something in this course. But this is what my statistic says. My statistic gives evidence to reject that, or I can't reject that. I don't have evidence to claim that you learned something in the class. So if the null is true, but I reject that, so that is you didn't actually learn anything, but I said you did, that's an error. That's a type 1 error. And again, if you didn't actually learn anything, but I said you did, that's a type 1 error. If you did learn something, the null is false, and I reject the null, that's correct. I should. The null hypothesis is false, and I rejected it, and that's a good thing to do. If the null hypothesis is true, so you didn't actually learn anything, and my statistic said, well, you didn't actually learn anything, then that's a correct decision. And if you did actually learn stuff, the null is false. But I didn't conclude statistically that you learned stuff, I made an error, and that's a type 2 error. So the best way that I know to describe this is a court case. So a court case is a really, really good analogy for this whole thing. You're either innocent or not innocent, but on trial you can be considered guilty or you can be let go. So innocent, nothing's going on, is a great example of the null hypothesis. And not innocent, something's going on, is a great example of the alternative hypothesis, or that the null hypothesis that you're innocent is false. And this is a really good case because typically we assume innocent till guilty. So we assume the null hypothesis until there's evidence that the null hypothesis is false. So we go into a study assuming the null hypothesis. Now in this case, you're innocent until proven guilty. So if you're innocent, but the jury declares that you're guilty, so on the left side here is the jury declares you guilty or acquits you, and then you're actually innocent or not innocent, that's the top. So if a jury declares you're guilty, but you were actually innocent, that's a bad thing. That puts an innocent person in prison, and that's the type 1 error. Now, if you weren't innocent and the jury declares you guilty, that's a good thing. That puts a guilty person behind bars. We like to see that. That's a good thing. Now, if you're innocent and the jury lets you go, that's a good thing. That lets an innocent person go. We like to see that. But if you're guilty, if there's actually something going on, but our test or our jury doesn't find out that something was going on, that's an error. So if you were actually guilty, but our jury let you off, that's an error. Now, that might not be quite as bad as putting an innocent person in prison, but this is letting a guilty person go free. That's not necessarily a good thing either. So what we do in statistics is typically we make the type 1 error the worst kind of error that we can have. So we want to really make sure we control this type 1 error. Remember from our discussion of confidence intervals that the type 1 error is alpha. So this is that alpha rate, that 0.05 we talked about, the percentage chance of making an error. We've already talked about this concept previously. That's alpha. We aren't going to go into this, but you can think of the sample size as the amount of evidence, and then something called effect size, which we're not going to go into at all in this class, is kind of like the strength of evidence. But I really, really like this analogy because it extends not only for this case, but for higher level statistical concepts such as sample size and effect size. So the level of significance, we already talked about like a 95% confidence interval where there's a 0.05 chance of an error. That's what we're talking about. The 0.05 chance of an error is a 0.05 chance of a type 1 error. And again, we call this alpha. So the probability of a type 1 error is that alpha. And now the probability of a type 2 error, we're not going to focus on super heavily in this class. It's covered by the Greek letter beta. And this has to do with something called statistical power. 1 minus this beta is statistical power. We're not going to talk about that, but it is a very fascinating conversation for a different time. At the beginning of the study, we determine our alpha level. That is, what is an acceptable rate of type 1 error? We talked about this with the confidence intervals without really going into detail about what all these terms mean. Typically, alpha of 0.05 is used in many kinds of research. Again, there's been some question called on that by the American Statistical Association and many researchers, but it is traditional to use, and it's not as terrible as maybe you'll read about if you're into this. So the critical value is something that we're going to use, and I'm going to go to my fancy iPad here. And this separates what we call the critical region from the non-critical region. So pretty much what we do is we look at one of these normal curves that we've had earlier. And we take this curve, and in looking at it, we separate values that are just too different to be considered from this group. So let's say if you're way out on this end, I just really think that you are too far out to be considered part of the main group. Whatever cutoff is used here, this is our critical value. Now, critical values can be on one side. They can be on the other side too. They could be on the left side instead of the right side, or they could actually be on both at the same time. This depends on your hypothesis. If your hypothesis was a less than hypothesis, you thought your hypothesis, should be further down. So let's say we had a mu less than whatever number. I'm going to say 19. I literally just made that up. You can put in your favorite v value. Then your curve is going to look, you're going to be looking at the left-hand side of the curve only. Now if you're, let's change to a different color, mean, and I'm just going to keep using mean, let's say greater than 19, but again, this could be any number, then you're going to be looking at the right-hand side of the curve only. Ignore the black. Now, let's say your mean was not equal to 19. I wasn't sure which side to go on. We're going to have a cutoff on both sides of this curve. Now the cutoff's going to be a little smaller because I'm putting the same amount of area in both sides. We'll talk about that in a sec. But I would have a cutoff on both sides where both sides could just be too extreme for me to believe that this came from that main distribution. So this is what we call our critical rejection region. Those highlighted regions are regions where the values are so different that we view them as being different enough from the main group for our conclusions. We can call everything that wasn't shaded in one of those colors the non-critical region. That's the values where we don't have enough evidence to believe that they're just too far out to be part of the main group. So it might be a little different from the mean, it might be a little different from some of the other values, but it's just not different enough to believe it's from a whole different group. So one-tailed test, and again, we just kind of drew this out, but the one-tailed test indicates when the critical region is on one side of the mean. So in a right-tailed, we're looking at values that are greater than. And again, note that there's no other color here. There's just one side. So if I think that the value is greater than the mean, I'm just looking at the greater than side of the distribution. And vice versa. If I think that the value is less than the mean, I'm just looking at the less than side of the distribution. Now this is the same as the image I drew up, but just to clarify, there's no other side here. If I'm looking at a left-tailed test or a less than test, I'm not looking at both sides. There's just one side that I'm interested in here. And finally, if I'm looking non-directionally, I want to split evenly between those two sides. Now because I'm splitting that area between the two sides, that area is going to be slightly smaller on each of the sides, but I'm going to have two sides here that are just too weird for me to accept that they're part of the main group. So for those critical values, how do we find those? Typically, we assign a cutoff of 1%, 10%, or 5%. Typically, it's going to be 5%. We'll change it up in class, but professionally, you're going to see 5% very often. For a left tail test and a right tail test, I've calculated the z-values for you. This just came from A2. You're welcome to use this if you want to. You certainly don't have to. Note that for the two-tailed test, these are both positive and negative. So remember, on the curve, we've got a cutoff on the left and a cutoff on the right. So for the cutoff on the left and the cutoff on the right, it's going to be positive 1.65 on the right and negative 1.65 on the left if our alpha is 0.10, and so on and so forth. All right, so if we want to draw this out, and we already did this, so you can look at our previous graphic. If the test is left-tailed or less than, then we're going to be looking at the critical region on the left side of the mean. If it's right-tailed or greater than, we're going to be looking on the right side of the mean. And if it's two-tailed, we're going to be looking on both sides. But the interesting thing is looking at this type 1 error. When we look at the area on the left or the area on the right or the area on both, for the area on the left, we'd be using alpha if it's a one-sided test on the less than side, or if it's a greater than on the right side, we'd be using alpha. But if it's a two-tailed, we're going to be using alpha over 2. That is our type 1 error rate is going to be split evenly on both the left and right side of the mean, and this is why those pink values were a little bit further out, is because we are using alpha over 2 instead of alpha. The area on each tail is a little bit smaller because we're splitting that area on both the left and the right. So if we're using the z-value, we can use the tabled value for z on the left. Now, if we're using the right hand, we need to find an area of 1 minus alpha below that. So let's draw this out real quick. So if I'm using a right-tailed test, and I want alpha to be on the right side of this z-value, then on the other side, I'm going to need to use 1 minus alpha so that I can find the z-value. Now remember, this is what's going to be in my statistical table, is the area on the left. This is what I'm going to get out of my statistical table. So this is what I'm going to use if I'm calculating a z-value with area on the left instead of area on the right. So when my alpha value is on the right, I need to use this 1 minus alpha to find the area on the left to calculate my z-value. And if it's in between, I'm going to need to use both. I'm going to need to use that alpha over 2, going back to our image. If it's in between, I'm going to need to use, for each of the two cutoffs, so I've got a two-tailed test. I'm taking my alpha and I'm splitting it. Part of the alpha, half of the alpha, is going here. Half of the alpha is going here. So for this z-value, I can just look up alpha over 2 to find this z-value. But for this one, I'm going to have to look up 1 minus alpha over 2 in order to be able to find what this cutoff score is. So remember our previous z-values from Chapter 6 and Chapter 7 when we were using them to be able to calculate these particular values from the table. But just make sure you're following along with how we calculate each one of these, and we'll do an example in a sec. In our next video, excuse me. All right, closing out here. The hypothesis testing problems the traditional method. So first, the steps, we state the hypothesis and identify the claim. So the very first thing that we do in each one of these problems that we have is we state the hypothesis and identify the claim. So we state the null and alternative hypothesis. Then we find the critical value. So if this is a z problem, we use the z table. If this is a t problem, we use the t table, and we find the critical values that we're going to be using to test our hypotheses. We're going to compute the test statistic, and we'll talk about what the test statistics for each of these are in a bit. We haven't talked about any of these yet. We'll make the decision whether to reject or not reject the null hypothesis. We'll talk about that. That's comparing the test statistic to the critical values. And then we'll summarize the results. So this is our hypothesis testing steps. Now, in order to make the decision as to reject or not to reject, step 4, we're going to be comparing the test statistic to the critical value. So if this is a greater than problem, we think the mean or whatever parameter, proportion, variance, whatever, is greater than some number, then we're going to be seeing if our test statistic is greater than the critical value. If it's the opposite, if we assume that our parameter is less than some number, mu is less than 23, whatever, some number is going to be plugged in here from our problem. If we assume that, then we're going to be examining if the test statistic is less than the critical value. Now, if it's not equal to, remember that we have two critical values. We've got one on the right end of that distribution and one on the left end of that distribution. So we're going to see if the test statistic is on the outside. So going back to our image, we're looking to see if the test statistic is in these shaded regions out here on the left or the right. So we're going to see, is the test statistic less than the small one, or is it greater than the big one? That's what we're going to be looking at in the test statistic on a two-tailed test or a non-directional test with a not equal to. Again, this is the one that I tend to lean towards if I'm not quite sure what I should be using. Tends to be appropriate in a wider variety of cases than the other two. Again, this is just a way to describe what we were already drawing out, but this is an equation form, maybe more helpful. Now, when we make this decision to reject or not reject the null hypothesis, it's important to remember something. We never accept the null hypothesis. We either reject the null hypothesis or fail to reject the null hypothesis or don't have enough evidence to reject the null hypothesis. This comes from the idea of a court case. Consider a court case where we're trying to prove someone guilty of murder. If we have enough evidence to prove them guilty, then we declare guilty. If we don't have enough evidence, then we declare not guilty, but this isn't a proof of innocence. This is not enough evidence to declare guilty. In the same way, in statistics, and this is in a wide variety of statistics, most statistics that are commonly used in research. In statistics, we're trying to acquire a body of evidence to determine the null hypothesis not true. So we set up this null hypothesis, and we're trying to determine that that's not the case or no longer the case. We either have enough evidence to make that claim or we don't. But if we don't have enough evidence to make that claim, it is not proof that the null hypothesis is true, just as not having enough evidence to declare someone guilty is not proof that they're innocent. It's simply not having enough evidence to prove the claim. So in this case, in statistics, we tend to be very strict about saying we either reject the null hypothesis, that is, we had enough evidence to prove that someone was guilty, or we fail to reject the null hypothesis. That is, we didn't have enough evidence to prove that someone is guilty. This has been a quick introduction to the steps in hypothesis testing. In the next video, we're going to talk about how we actually perform one of these hypothesis tests and hopefully help a lot of this make sense by starting with the z-test for the mean. Again, z-test is assuming that our standard deviation is known.